Chipmaker ASML uses polarized light passed through a polarization-maintaining fiber to measure lithographically printed features on semiconductor wafers. The goal of this project is to investigate if unpolarized light can pass through a PM fiber unaltered by measuring quasi-monochromatic unpolarized light piped through a fiber delivery system as compared to a theoretical physical model.
Optical fiber transmit light through a flexible glass core, which is surrounded by a glass cladding with a lower refractive index than the core to keep the light trapped in the fiber. Since light is an electromagnetic wave, its electric field has some direction, which is its polarization state. And if that polarization state is randomly fluctuating or composed of equal amounts of orthogonal components, it is said to be unpolarized.
Polarization is affected when light travels through a birefringent material or polarizer. Birefringence is a material property where the refractive index depends on the light's polarization. Our polarization-maintaining fiber and the fiber we use for the light delivery system are both single-mode. This means they are designed with a small core and the geometry required to transmit only the fundamental transverse mode of light, which oscillates perpendicular to the fiber.
The light incident on the PM fiber must be unpolarized Gaussian laser light in the visible wavelength, so we must depolarize laser light before coupling it into a single-mode fiber. The single-mode fiber that delivers this light to the PM fiber must be step indexed with a numerical aperture around 0.1, and the PM fiber numerical aperture should match as close as possible. The output from the PM fiber should also be Gaussian, with as close to 0 degree of polarization as possible and no extra polarization loss within the fiber. We must create a theoretical model to describe how polarization is affected by the propagation through the fiber, which we should verify through experimentation.
To solve this problem, we have developed a theoretical model based on Euler matrices which describe the action of an optic on the polarization state of light. We developed an experimental model in parallel with a theoretical model backed by research and testing throughout the year. The experimental model consists of light depolarization, fiber coupling and propagation, and a measurement system at the output. Since measuring the polarization state of light and measuring the action of the optics on that light require different setups, we focused on building a Stokes polarimeter to measure the light field. To measure the optics, we collaborated with the Polarization Laboratory at the Wyant College of Optical Sciences.
The theoretical model describes the light propagation in fiber, which is based on the Stokes vector and the mu matrix, which representing the property of the light and the PM fiber respectively, and the interaction of them will help us predicting the light output from the PM fiber. We will experimentally measure the property of the PM fiber and adapt those into our theoretical framework, and this allows us to convert our general form into the numerical mu matrix.
Unpolarized light isn't necessarily a thing in itself, rather it is the superposition of a bunch of known polarizations that are just random. Degree of polarization is essentially a measure of how random that light field is, or in other words, it's a measure of does it have any preference toward one state of polarization as opposed to complete randomness in all directions.
We use a liquid crystal polymer depolarizer to depolarize our light in free space. A liquid crystal is a birefringent material, so we can adjust its phase axis to make different kinds of wave plates. And the LCP depolarizer components with lots of tiny strips of different wave plates. And when the light passes through it, the light will be divided to different strips of light and different kinds of polarization states.
Basically, you have a bunch of liquid crystals sandwiched between two pieces of glass, and they all act as micro-retarders. So you introduce about 2 degrees of polarization change across the entire beam that you send through the liquid crystal depolarizer.
With a larger diameter of laser beam, it can pass through more different kinds of wave plates to get more kinds of polarization states of light. We have a fiber pod coupler, and it has a small lens inside that can help us to calibrate the laser beam from free space into the fiber. But the coupler designed for mount on the laser, so we designed the mounts make it can work on optical rail and can move it on optical rail that can let it work in free space optical system.
A Stokes vector is a 4-element vector that describes the polarization properties of light. The first element is total intensity, second element is X versus Y polarization, third element is 45 degree versus negative 45 degree, and fourth element is right circular versus left circular polarization. The Stokes polarimeter consists of a light source, which you're trying to measure the polarization of, a linear polarizer fixed at 0 degrees, a quarter wave plate which you rotate, and then a detector of some sort. In our case, we used a photodiode connected to a power meter. It works by changing the angle of the quarter wave plate, which adjusts the polarization configuration of the elements, and then you take the power readings that you get at each of those configurations and then perform some math on that to determine the Stokes vector of the input light. You take those power readings that you took, and then you can either multiply them by what's called a data reduction matrix, or you perform Fourier analysis on those power readings and you get your Stokes vector.
We took 3 sets of measurements for each setup at angles between 0 and 160 degrees in increments of 20 degrees. First, we measured the depolarized light. Then, after propagating through a single-mode fiber alone, the PM fiber alone, and the single-mode fiber coupled to the PM fiber,
we were able to achieve an average degree of polarization for the depolarized light of around 10%. After propagating through the single-mode fiber, the average degree of polarization was about 92%. The PM fiber alone showed an 82% degree of polarization, and for the fibers coupled together we measured an average degree of polarization of 88%. This means that neither single fiber is fully propagating the spatially depolarized incident light.
The beam size of our depolarized light is larger than the ideal incoming beam size for the lens that couples light into the fiber. Only a portion of the depolarized light is coupled into the fiber. There is a minimum area required to cover the full range of polarizations created by the liquid crystal depolarizer, but the low coupling efficiency and small core size mean the fiber can only receive a small part of the depolarized light, which only covers a limited range of the polarization states created by the depolarizer. This means the light is effectively not unpolarized anymore.
We used a visual field locator to test the amount of depolarized light that actually enters the fiber. The degree of polarization of the depolarized light was about 10%, meaning about 90% of the beam is made of different kinds of polarized light. With about 17.5 coupling efficiency, the percentage of spatial depolarization accepted by the fiber was about 15.5%, so we would accept the output light to have a degree of polarization about 84.5%.
the polarization lab was nice enough to let us use their Mueller matrix polarimeter. We had a system consisting of a fiber port, polarization maintaining fiber, and fiber collimator. Another system where that polarization maintaining fiber was substituted for a single mode fiber, and a third system which just consisted of the 2 coupling optics. And we went in there for a few hours and they let us take the measurements of the Mueller matrix of all those different elements. So Stokes polarimetry is light measuring polarimetry, whereas Mueller matrix polarimetry is sample measuring polarimetry. Stokes polarimetry only uses a polarization state analyzer, a PSA. You can have any light field coming into it, it does not matter, and it'll essentially analyze the light field that is coming out. Mueller matrix polarimetry needs a polarization state generator and analyzer. It essentially sends in known states of polarization into a sample, and then it can analyze those states coming out of the sample to see how they changed. And based on a sequence of measurements of known input polarization states and measuring how they came out on the output, we can essentially tell how that sample manipulated the light field and therefore fully characterize its polarization effects.
While the theoretical dye attenuation Mueller matrix is very similar to the experimental one, the other 2 Mueller matrices regarding the retardance and the depolarization are different from the experimental results. Thus, it leads to the final Frobenius norm value of 2.6, which is relatively large. This difference could be due to bending and twisting introduced during the experiment, which contributed extra retardance and depolarization. This was inevitable due to the limited space for experiments.